Hi, everyone. Welcome and thank you for being here. I'm Max Odkins with the Fire and Resource Assessment Program here at CAL FIRE. I'm very excited to welcome you today to this presentation that's hosted by our Forest Health Research Program. We're joined today by Dr. Adam Kochanski from San Jose State University for this presentation, Coupled Fire Weather Dynamics, the interplay between convective plumes, wind patterns, and fire behavior. Before we get started, I do have some brief housekeeping. So as I mentioned, this meeting is being recorded and it's going to be posted on our website. You can find it at the URL that's listed on the slide or using the QR code that's there. It will be posted most likely a few days after this presentation, but you can also find recordings of our previous webinar presentations at the same website. We are going to have a question and answer period after the presentation, and you can participate in that by entering your questions in the chat at any time, or you can raise your hand and we'll moderate that Q&A at the end and allow folks to unmute to ask their own questions when we get to that point. So before we get started, I did just want to briefly touch on the Forest Health Research Program here at CAL FIRE. We are, sorry, just a second here. Great. So the Forest Health Research Program is designed to prioritize and fund research in forest health and fire science critical to the state of California, and share that scientific information and support statewide plans, including the California Wildfire and Forest Resilience Action Plan, as well as other statewide plans. To date, we have funded 89 competitive grants for about $31 million, and we are anticipating opening a new solicitation for this grant program in October of this fall. So please keep an eye out for announcements related to that. We are going to have more information about that. You can find it on our website for the program, and you can also sign up for email updates about the solicitation or other important updates about the program at the URL that's listed on the slide or the QR code that you can see there. With that, I am about to turn things over for our presentation. I'm very happy to introduce our speaker for the day. Dr. Adam Kochanski is an associate professor at San Jose State University, leading wildfire modeling efforts at the Wildfire Interdisciplinary Research Center. His work centers on fire-atmosphere interactions, fire behavior, and air quality impacts, aiming to enhance fire and smoke forecasting. A co-developer of the WRF S-Fire model, Dr. Kochanski works on advancing predictive capabilities and strengthening community resilience against wildfires. Thank you very much for being here today, and please take it away.
Right, great. Thank you very much. My name is Adam Kochanski. I'm associate professor and the lead of the modeling group at Wildfire Interdisciplinary Research Center at San Jose. And I would like to thank for the opportunity to present our research here. And I would like also to acknowledge funding that we received from CAL FIRE to conduct those numerical experiments that I will be showing you later today. So let's move on. I would like to start from a quick outline of this presentation, and essentially here what we will be starting from is going to be just fire environment and winds, and we will be talking a little bit about what those winds are and how they differ near the fire front, away from the fire front. And later on, we'll talk a little bit about coupled fire atmosphere modeling, because that's what we will be using to investigate fire effects on the atmosphere. We will start our investigation at small scales, and we will be talking about prescribed burn, and that's going to be fire flags experimental burn. And later on, we are going to move into larger scales. So we will be trying to investigate fire winds associated with wind-driven fires and plume-dominated fires. And we'll be talking specifically about the Thomas Fire and the Creek Fire. And later on, we'll talk a little bit about different effects. We'll be talking about what else may happen when we have a fire. We'll be talking about other modifications that may change local fire environment. We'll be talking a little bit about interactions between the fire and hydraulic jump during Lahaina fire. And we'll be also showing some examples how a fire can also modify precipitation and also impact the fire behavior through this type of interaction. So the very first thing that we have to start from is, of course, the fire environment. And here in particular, I will be focusing on the weather component here. And of course, we know that we have strong influence of wind, temperature, relative humidity, precipitation, and atmospheric stability in the context of creating the fire environment. But in this particular presentation, I will focus mostly on two of those. I will be talking about winds, fire-induced winds, and I will be talking a little bit also about fire-induced precipitation. So if we think about the importance of those weather elements, they will also be very critical in the context of affecting fire behavior. And those factors like wind speed, steepness of slope, fuel moisture, fuel type, those are going to be the primary factors controlling fire behavior. Now, the interesting thing is that typically we would consider those factors as external factors or not related to the fire itself. But what I'm going to show you today is that it's not entirely true, because the wind actually can be modified by the fire itself, and the wind interacting with the fire front is not going to be the same as the wind measured some distance away from the fire. And also, we may have modification of local weather conditions that will be important in the context of the fire propagation, because at the end of the day, it's not going to be the wind some distance away from the fire that controls the fire propagation. It's going to be the wind near the fire at the mid-flame height, really impacted by the fire itself. And also, we will be talking a little bit about the fact that fuel moisture, which is extremely important in the context of fuel flammability, fire intensity, and the rate of spread, can also be affected by the fire activity. And we may have some impacts because of, for example, enhanced precipitation due to the fire itself. It's not that easy to really investigate those effects. And what we will be doing in this presentation, we will be essentially trying to leverage coupled fire atmosphere model, WRF fire, to investigate all those interactions. However, before we go into that, we need to start from what are uncoupled models and what are coupled models, just to get an idea about what is the difference and why we can use those coupled models to investigate fire effects on local fire environment. So in a classical scenario, if you think about uncoupled models, you will have a fire model, and this fire model is going to receive information like a weather type, like wind speed, temperature, and that would be like external source of data being fed into the fire model. The fire model may also use information about slope, fuel type, fuel moisture, and this, a consequence of its computations is going to generate fire spread forecast. And here we'll be talking about models like Behave, Farsight, Prometheus, FSPRO, and many others. Now, there is a different way how you can do that. You can also try to do that in a coupled sense. And in the coupled sense, what's going to be happening is that we will have a fire model. And the fire model that you see here is going to be two-way connected with the weather model. So they are going to be connected in this loop. What this loop is going to be doing is going to allow the heat and moisture fluxes generated by the fire model to be fed into the weather model, and this coupled weather model is going to respond to the heating and moisture fluxes and smoke injected from the fire model, and the modified local environment and modified local winds near the fire front are going to be used to drive the fire propagation. So that's going to be the first loop, which is realized within the coupled fire atmosphere model. And the other loop is going to be this bigger loop through the fuel moisture, because we may also have modification of the amount of clouds and precipitation as a consequence of heat and moisture fluxes coming from the fire itself. So this rain and atmospheric humidity impacted by the fire itself is also fed into the fuel moisture model, and then changes in the fuel moisture are then here taken into account by the fire model responding to those changes, and that's the second level of coupling in a coupled fire atmosphere model. So at the end of the day, if you think about what is specific here in those coupled models, is that the fire itself is going to affect local weather because of those heat and moisture and smoke fluxes. So local fire affected conditions are going to be used to compute how the fire progresses. And of course, at the end of the day, if you think about what you can get from a model like that, it's going to be, of course, fire spread forecast. But because of this coupling, you also will have high resolution local weather forecast, accounting for the fact that local weather may be changed because of the fire itself. You may have fuel moisture forecast and smoke forecast as well. So in practical terms, if you think about what you can get out of a coupled fire atmosphere model, it's going to be something which is here shown on this animation on the left side. So you see here we have a fire propagating on the surface. It generates heat, it generates smoke. This heat is injected into the atmosphere. We see that the atmosphere responds to this heating. We have this buoyant updraft. Here we have perturbed circulation ahead of the fire. We have smoke, all of that as a result of the fire atmosphere coupling that we have realized in this model. So now you may ask a question, okay, do we have any data, any experimental observations that would highlight those fire atmosphere interactions and help us identify, how strong, how important those effects are? And the answer is yes, to some degree. We have data from Fireflux and Fireflux 2 experiments, and those were grass fires, very well instrumented. In particular, we had here a very tall tower, 30-meter tower with multiple anemometers at various heights, also with thermocouples measuring the temperature. So essentially what this kind of a setup allows you to do is to investigate what happens as the fire propagates, and as the fire passes through the tower, we can actually measure what were the winds driving the fire propagation, what were the winds at the fire front itself, not away from it, but exactly what was the fire environment during the fire front passage. And we can then try to use numerical simulations to reproduce the same scenario, and we can learn from those numerical simulations about the importance of fire atmosphere coupling processes. In this particular case, we were measuring winds at 3 different heights, and we were also measuring temperature, moisture fluxes, momental fluxes, etc., etc. But what I want to point your attention to is that here is the map at the bottom that shows the wind vectors at 3 different levels. That's 5 meters, 10 meters, and about around 20 meters. Here, the color corresponds to the temperature. So here, this core, this yellow color, corresponding to temperatures like close to 350 degrees of Celsius. That's what was measured at 5 meters above the ground and a little bit lower by our thermocouples. And the interesting thing is that if you look closer at the winds during the fire front passage, you will see that something unusual happens, because normally we would expect to have winds stronger above the surface, aloft, and weaker near the surface. But here it's exactly opposite. So you see very strong winds here during the fire front passage being formed near the surface, and we have much weaker flow aloft. So definitely something changes as the fire moves through the landscape, and this fire environment is clearly impacted by heat and moisture fluxes generated by the fire itself. So now you make us a question like, okay, so can we measure those fire winds directly? And the answer is no, we cannot, because what we measure, even if we have instrumentation like the one showed here, we can only measure the overall wind, which is going to be the overall wind impacted by the fire itself. So it's going to be essentially superposition of ambient winds and fire-induced winds. So we will see what is the overall wind, but we are not going to be able to say, okay, what fraction of it is really something induced by the fire itself. However, what we can do is we can run numerical experiments, and we can run those simulations with and without heat fluxes being injected from the fire to the atmosphere. And then we can compare simulated wind field from a simulation with and without fire, or a simulation which is coupled and uncoupled. And based on that, we can assess and just compute the difference between the wind speed in, for example, those 2 simulations. And this difference between the coupled and uncoupled simulation, that's going to be essentially our fire-induced wind. So by doing that, we can quantify the effects of fires in the context of wind speed, but also any other variable that we have in our model. And we'll be doing something very similar also for precipitation. So here's an example of 2 simulations for the Fireflux experiment, uncoupled simulation on the left side and coupled on the right one. And you see right away much stronger winds here, reaching like 14, 15 meters per second, much more fluctuations, change direction, also because of the fire itself. So clearly the pattern of the winds here changes because of the fire itself. The wind speed becomes much more variable in this coupled simulation. We have fire-induced winds, which are here reaching 14 meters per second. That's 30 miles per hour, so pretty significant. And also, as a consequence of that, you see that the simulation on the right side reached the end much faster than the uncoupled simulation, which indicates that those fire-induced winds are important in the context of the fire progression. So now you may ask a question, what is happening here and why this coupled simulation actually was faster than the uncoupled one? And in order to investigate that, what we are looking at here is the cross-section in the direction perpendicular to the wind, and that's what you see here on the left side. So essentially, that's the vertical cross-section showing the updraft, and you see this core of really strong vertical velocities aloft. And here on the right side, that's the cross-section in the wind direction through the plume. So fire is somewhere here, and here you see this convective column being formed because of the heat and moisture fluxes generated by fire. If you zoom in over the region of the fire itself, you will see that that's the heat profile. That's where fire releases heat into the atmosphere. And you will see that the column here that forms this buoyant plume is really strong, and also it's what drives near surface winds. So we have the buoyancy which generates this convective updraft, but also what we see here is that this convective column is being pushed downwind from the fire itself. And that's very critical because due to this displacement, you will see that we will have inflow into the convective column, and this inflow into the convective column is gonna enhance surface winds, and that's what's gonna essentially be the cause of the wind change near the surface, and that's why we will see those winds near the surface, as you see, much stronger than aloft. That's going to be just the impact of the inflow into the convective column, essentially generated by the fire itself. The same thing we can also observe looking at wind speed observations during the fire front passage. And what you are looking at here is just the ambient wind profile away from the fire. And you see that that's a typical logarithmic profile with weaker winds near the surface and higher winds aloft. And we have a pretty good representation of those ambient conditions from our simulation, from this ambient wharf, as you see, very close to observations. However, something very interesting happens once the fire passes through the tower. And what happens is that we have this shift in the winds, and we have this wind profile that is flipped. And instead of having the typical scenario when we have stronger winds near the aloft and weaker winds near the surface, then the situation becomes absolutely opposite. So you see those red lines indicating that the winds near the surface becomes stronger than the winds aloft. And that's exactly associated with this inflow into the convective column that I showed you on the previous graph, and the fact that the buoyancy induced by the fire is strong enough in this case to completely flip the profile and change the vertical atmospheric structure and lead to this, if you will, low-level jet induced by the fire itself. So if we want to sum up here what we learned from those small-scale experiments, we learned that we have strong modification of surface winds because of the fire itself. We also learned that everything is linked to this convective activity and the formation of the convective column, which is displaced a little bit downwind from the fire. And that allows to create this cross flow through the fire front. And at the end of the day, that's what modifies the propagation of the fire itself. So that's great. I mean, we have some idea about what is happening at small scales, but how would that look if we are interested in a wildfire scenario? So here we'll be looking at a very similar analysis, but performed for a wildfire event, and we will start from the wind-driven Thomas fire. The Thomas fire started on December 4, 2017. And it was one of the largest wildfires in California history. It burned almost 300,000 acres. It took over a month to contain this fire. It destroyed over 1,000 structures. So it was a very significant event. If you look here at this animation, you will see right away that this fire originally started moving very, very fast to the shore, and later on it slowed down a little bit when the winds became weaker. So we will be looking at this particular scenario, at this particular fire, trying to analyze how strong those fire-induced winds were during the Thomas fire. So the way how we do it is very similar to what I showed you before. So we have simulations with and without fire, and we compare the wind speeds from these two simulations. Every other aspect is identical in both simulations. So direct comparison between those two simulations allows us to assess what are the regions of accelerated and decelerated flow, and that's what you see here on the right side. So you see here all those pink colors, they correspond to regions where we have significantly stronger surface winds because of the fire itself. Those green patches, they correspond to the regions where winds are actually weaker. Here at the bottom, you also see a vector plot. Actually, there are two sets of vectors, blue ones from the uncoupled simulation and the red vectors from the coupled simulation. But here you don't really see that much of the change in terms of the wind direction, and that's why you have only slightly differences between those two vector fields. However, what is important here is that, first of all, even though we are talking about the wind-driven fire, so we don't have a classical kind of chimney effect here. You saw on the animation, it is a little bit messy. The plume is very tilted, but still the heat released by the fire is significant enough to modify local weather and modify those local winds and create disturbances, let's say up to like 6 meters per second. Another really important thing is that we have very strong non-local effects. You would expect that if that's the fire, kind of outlined here with this black contour, that you would have those fire-induced winds exactly where you have active fire. But in this particular case, it's not the case, because you see that most of the effects are actually non-local, and it's the modification of the winds downwind, a little bit here to the north, to the northwest from the flank. Those are the regions that experience the highest wind speed perturbation induced by the fire. Also, that's something that would be very important for us in the context of, for example, behavior of the spot fires, because if you imagine that you have a spot fire and embers just landing ahead of the fire front, they would experience significantly stronger winds, and as a consequence of that, they would just propagate much faster. So now let's take a quick look at the mechanism, what is happening here. So the very first thing that we need to acknowledge is that this fire event was strong enough to significantly modify local weather conditions. Here at the top panel, what you are looking at are the vertical velocities induced by the fire itself. So those orange colors, they correspond to the vertical movement of air induced by the fire, and the purple one corresponds to the downdrafts. And here at the bottom, the red and blue color corresponds to the wind acceleration or deceleration. So those red points, they correspond to accelerated winds, and the blue patches, they correspond to decelerated winds. And we also have two set of lines. Those are isotherms without the fire. Those are the blue lines. And from the simulation with fire, those are the red ones. So a very important thing that we see here right now is that we have those bands of downdrafts and updrafts, and you can see them here, first two, and here if you look at the cross section in the direction perpendicular to the wind. So the first column is in the direction of the wind as indicated in this insert, and on the right side, that's the cross section in the direction perpendicular to the wind. You will see that we have those bands of updrafts and downdrafts. And not only that, but if you look down, you will see that essentially those regions of downdrafts, those are the regions where you would expect also acceleration in the winds. That's where you see those red colors. And in the regions of updrafts, you see more of the blue color, so you see a little bit of deceleration. And one other important thing is that you also see a significant modification here in this wave, and you see that the modification of this wave actually propagates here also downwind. And that's why you also see those non-local effects, because it's not just what happens over the fire itself, but you have this propagation of the disturbance within the gravity wave, and that leads to those non-local acceleration and deceleration zones formed far away from the fire front itself. If we look at the vertical cross-section of the flow, and if we look at where the winds are strongest, you will see this very well-defined wave pattern. Here you see the outline of the fire itself. And you see that kind of upwinds from the fire, you generally speaking have those regions where you have stronger winds above and weaker winds near the surface, those greenish colors. However, then once you have interaction with the fire itself, that changes a little bit, and the wave itself gets modified, and you will see how it evolves in time. We will have the growth of the fire, the stronger heat fluxes become also the more modification we see here in this wave pattern, and that's the mechanism of changing winds near the surface. You can also see that on this figure showing just the difference between fire and non-fire simulations, or in other words, just the zones of accelerated and decelerated winds. And you see that in general, what happens is that we have acceleration of the winds near the surface at the expense of the winds aloft. So those winds above get weaker, and the winds near the surface get stronger, and that's because of those vertical movement induced by the buoyancy generated by the fire itself. So if you look at this animation, you will see at the beginning we don't see any fire effects, and then as the fire progresses and it becomes more and more intense, also the modification of the wind field becomes more intense, and we will start seeing those patches of accelerated and decelerated winds. And of course, that was going to be important in the context of the fire progression. All right, so we see that, but we would like also to quantify and to make sure that when we look at those fire effects, we have a good grasp of the character of those changes, and we want to identify if they are local or non-local, and that's what we are doing here. So we are essentially trying to check what are the mean wind speed differences between fire and no fire simulation at the local scale, which in our case is within 5 kilometers from the fire front, and the non-local just far away from the fire. And you see here, especially during the first day, that we have those local differences in the wind or the strength of the fire-induced winds during the first day, which are significantly lower than the strength of those non-local winds. So essentially, it tells you right away that those non-local winds are here dominant, especially during the first day. And that's kind of what is consistent with the idea of this disturbance propagating within the gravity wave and then impacting surface winds. You may also take a look at how those fire-induced winds changed over time. And here are the time series of the maximum fire-induced winds. You see that on the left side, and the mean fire-induced winds on the right side. So essentially, there is not much here diurnal pattern, but you see that you have significant increase here in the magnitude of the fire-induced winds as the fire progresses. So this first day when the fire rushes really quickly and is very intense, this period is associated also with very strong fire-induced winds. We are talking about winds as fast as 15 meters per second, so that's 34 miles per hour. So very significant impact of the fire on local winds, and of course important in the context of the fire propagation and what happens near the fire front, but also, as I mentioned, what happens downwind from it. So to sum up, what we learned from this experiment is that we have very strong fire winds in this case, even though that's a wind-driven fire. We have very strong non-local effects, which are important in the context of spot fires. And also the mechanism is associated with this disturbance in the atmospheric gravity wave that then propagates and impacts the wind field. So that was one case, a wind-driven fire, but now let's try to investigate how those fire-atmosphere interactions would work during a plume-dominated fire. And here we'll be looking at the creek fire, and the creek fire which started on September 4th, 2020. It burned close to 400,000 acres. It took more than 3 months to fully contain this fire, and it destroyed over 850 structures. So another very significant event. On the left side, what you see is a snapshot from the coupled fire atmosphere simulation for the creek fire. And what you see here is, first of all, that we had this very well developed convective column. Before, you remember when we looked at the Thomas fire, everything was tilted, diffused smoke. I mean, it was very difficult to even see the convective column. Here, the situation is different. We see well-defined convective column. Not only that, here on the top of it, you see this blue shading. This blue shading shows the cloud-water mixing ratio. So that's the indication of cloud being formed on top of smoke. So that's a pyro-CB cloud in this case. And not only that, but if you look here at this vertical cross-section and you look here at the colors corresponding to vertical velocities, you will notice these two very strong cores. And here within those cores, we are talking about vertical velocities reaching 20 meters per second or 44 miles per hour. So very significant disturbance in the wind field induced by the fire itself. So we here will be looking at a very similar thing as before. So we will be looking at the differences between fire and no-fire simulations for this particular case. And we will be doing that for 2 time points, one during the initial fire growth under moderate to weak winds, and later on when the winds were even calmer and the fire became 100% plume dominated. So the very first thing that we need to note is that if you look here at this figure, you will see that those disturbances in the wind field are here really much closer to the fire itself than in the previous case that we analyzed. There is a little bit of non-local effects. You see this kind of greenish shading here downwind from the fire. But generally speaking, you can tell right away that most of the fire-induced effects are confined to the region of active fire growth. If you look here at the bottom during the same time, you will see also that in this case, we will have way more differences between fire and no fire induced winds. You will see a lot of places where we have changed the direction because of the pyroconvection itself and the effects of the convective plume formed over the fire itself. If you look on the right side later on, you see that the wind pattern changes. So from southerly winds, here we go to mostly weak northerly winds. So we have fire activity on the opposite side of the fire, but still the same story is true. We have mostly perturbation here near the fire itself. We are talking up to 3-4 meters per second. We may have some slight patches of very modest modification downwind, but generally speaking, everything is way more localized. So if we think about the mechanism here, it's going to be a little bit different. We see right away that we have much stronger heating effects from the fire, and also we have more intense updrafts than before. In the previous plot, we had vertical velocities here in the wind plane up to 1.5, 1.6 meters per second. Here you see that we are reaching 3.2 meters per second, so that those vertical velocities are much stronger. So that's very important. But also you will see right away that we have here these regions of fire-induced downdrafts, and those regions of fire-induced downdrafts, like the one highlighted here, that's also where we will observe much stronger winds near the surface. So the regions of the downdraft here also are associated with acceleration of the winds near the fire itself. The difference here is that you see that those effects are way more local and everything happens near the fire itself, but not that much perturbation we see outside of the fire itself. Also, if you look here on the right side, you will see 2 convective columns here, and you will see really well-defined downdraft here between those columns, and also this downdraft here is associated with strong acceleration of winds here in this valley. And not only that, but you will also see that we have significant modification in the winds, and we may have some wind reversal. You see here, for example, in this region, with those red arrows pointing in completely opposite direction to the blue ones, indicating that the wind direction shifted by close to 180 degrees because of the presence itself. So those are those 2 regions. If we look a little bit later on, during this phase of really well-developed convective column, when the winds are a little bit weaker. We'll see also very significant circulation induced by the fire, and you will see that those winds are going to be way different here from coupled simulation and then uncoupled simulation. We will see those updrafts. We'll see also the downdrafts. We'll also see those well-defined updraft zones. In this case, you will see that in the plane of the wind direction. But also, you will see a very similar thing on the right side. And if you look closer into this picture, you will see a very similar pattern to what we discussed when we were talking about this idealized fire flux simulation. You will see those red arrows near the surface being much stronger than the blue arrows. So the blue ones correspond to no fire simulation. The red arrows correspond to the simulation with fire effects. And you will see here also this inflow into the convective column. And this inflow essentially changes the local circulation, leads to acceleration of near surface winds. So very similar effect to what we discussed during the fire flux experiment. The big difference again is here as you see, we have mostly local effects. We don't see that much remote effects. So everything is going to be confined to the region near the fire itself, where we have significant vertical circulation induced by the fire itself. If we look at the time series, we will see that in this case, we have slightly weaker fire-induced winds, around 11 meters per second or 22 miles per hour. But also the other interesting thing is that we will have some diurnal trend here visible. So in this particular case, this linkage between the fire and fire-induced winds is evident. And as the fire activity changes from day to night, we will also observe changes in the magnitude of fire-induced winds. In order to identify, again, those local and non-local effects, we did the same computation that I showed you before. We looked at the strength of the fire-induced winds locally near the fire and away from the fire. And here you see the opposite situation to what we discussed before during the Thomas fire. You will see here right away that those local effects, those blue bars, actually indicate stronger fire-induced winds than those orange bars, indicating the remote effects. So clearly, during a plume-dominated fire, those effects that we just discussed of the fire itself on local flow, they will have much more local character, and they will be important in the context of the fire environment and what drives the fire propagation. So what we learned from this experiment, we learned that we still have significant fire-induced winds during a plume-dominated fire, still up to 25, even 30 miles per hour. We see the diurnal cycle, but the difference is that in this case, we mostly have local effects, not non-local effects that we discussed during the Thomas fire. So now you may ask the question, okay, so is it everything? I mean, do we only have the impacts on winds or something else may happen as well? And the answer is that something else may happen. And in particular, we may have precipitation induced by the fire itself. So here, what you see on this graph, we have the total precipitation during the creek fire. And on the right side, you see just fire-induced precipitation, which is computed again as a difference between the fire and no fire simulation. So we see that here this fire-induced precipitation is significant. We have precipitation up to 5 millimeters just induced by the fire itself. So in this particular case, it's up to 50% of the total precipitation. So those are significant effects. The pattern itself doesn't really change. So you see that it's not that because of the fire, the rain happens in a different location. It happens in the same location, it's just stronger. So we have precipitation here, and it is enhanced mostly on the eastern side of the fire itself, as you see here. So now you may ask, like, okay, so why would that be important in a coupled fire atmosphere model? Well, that would be important because if we have increased precipitation, also we will have increased fuel moisture. And if you look here at this figure that presents the fuel moisture content, you will see a lot of dark blue and green colors exactly corresponding to those regions where we have precipitation. But more importantly, what happens is that this additional precipitation, which is induced by the fire itself, is important in the context of the rate of spread. And we looked at 2 days with the largest amount of precipitation, that's September 11 and September 12, and we see up to 13% difference in terms of the rate of spread. So essentially, additional precipitation induced by the fire increases fuel moisture and it reduces slightly the rate of spread. Here we are talking about the effects in the order of 15%. So that's great. So we have at least one mechanism that could slow down the fire. We may have precipitation, but the question is, are there any other possible scenarios where we wouldn't really have precipitation, but still the modification in the wind field would decelerate fire progression? And yes, it is possible as well under certain conditions. And here we'll be talking about the Lahaina fire, which started on August 8, 2023. It was much smaller. It burned about 2,170 acres, but it incurred tremendous damage. Over 2,200 structures burned and also close to 100 fatalities. So very significant event as well. You see that this fire is driven by the strong down slope windstorm, and the fire first propagates just downwind, pushed by those winds, and then it starts this lateral progression, and that's what we will be looking at. So if we look at the meteorological conditions during this fire, it was driven by downslope windstorm. And you see here those regions of very strong winds. So we are talking about 50 and 50 plus knots winds. And those zones of really strong winds were just pushed to the shore, very close to the Lahaina. And that's what was driving the initial fire progression. But not only that, you see here a lot of turbulence and a lot of rotation here near the coast. And those all turbulent eddies that you see here, they are formed and as a consequence of the interaction between the mean flow and also the hydraulic jump that I will show you just in a second. So here is the hydraulic jump. So you have this onset of the windstorm. You see that we have the beginning of the windstorm. Those stronger winds are here indicated in red colors. You see how it extends here offshore. And we have also a lot of turbulence here associated with this hydraulic jump itself. And the rotation that you see here and all those turbulent movements that are observed in this animation, that's what essentially was driving the fire progression after its initial run to the coast. So here is an example of that. You see on the left side the streamlines. This brown contour represents the extent of the fire, and you see clearly here those regions of strong rotation, and those kind of almost like counter-rotating eddies were really persistent here, and they were helping with lateral fire propagation. Later on, you could see they are even better developed, and they are easier to see. On both sides, you also see here this kind of southern component pushing the fire to the south that is also associated with the presence of the hydraulic jump. You see a lot of uniformity in winds here on the right side. And then here is this region of the hydraulic jump where you have all the mass and you have all those rotations. So if you look at the fire propagation itself, it just started here and just propagated toward the shore very quickly. So that was the origin, and within a few hours it reached the coast. And later on, after it reached the coast, I mean, it couldn't really go any farther downwind, so it started the propagation to the north and to the south. And this propagation, this lateral propagation, was associated with the hydraulic jump and the turbulence generated by the flow that I showed you just a second ago. So now you may ask a question if in this case the fire was strong enough to modify hydraulic jump, and the answer is yes. In this case, this fire was strong enough to modify the location of hydraulic jump. You see here in the uncoupled simulation, this hydraulic jump is directly over the fire itself, and you also see how it modifies here the winds. It creates this flow reversal. It also here creates some northerly component of the wind that would push the fire to the south. In the coupled simulation that you see on the right side, you see that the hydraulic jump is pushed more here toward the ocean, And as a consequence of that, the fire itself experiences more uniform winds. And the turbulence induced by this hydraulic jump is a little bit more downwind from the fire and has a lesser impact on the fire propagation. And you can see also the same thing here on the vertical cross-section of the winds. So here at the top, you see this hydraulic jump from uncoupled simulation, and at the bottom, you see from the coupled simulation. And the interesting thing is that you will notice here stronger winds near the surface here in the fire simulation. And that's consistent with what we know about how fires will modify local winds and create this near surface acceleration. But in this particular case, this acceleration of the flow near the surface directly interacted with the hydraulic jump. It pushed this hydraulic jump more offshore, as you see here. And as a consequence of that, the fire itself was impacted more by those eddies and the vorticity induced by the hydraulic jump itself. So you can also see that clearly here on this figure. So it shows in red arrows the winds during the coupled simulation and black arrows from uncoupled simulation. So you see that those red arrows are longer, indicating stronger winds in the coupled simulation. However, that's not what really is the key driver of the fire propagation in this case. You see that the extent of the uncoupled simulation, this black contour, is bigger than the red one. And the reason for that is that here in the coupled simulation, you see that we have way more uniform flow. And here near those edges, we don't really have much of the lateral spread. And we don't have much lateral spread because also we have less of the turbulence, we have less rotation and less influence of the hydraulic jump, which was pushed downwind from ahead from the fire itself. And as the distance between the hydraulic jump increased and the fire front, of course, the impact of all the rotation and all the turbulence within the hydraulic jump was reduced, and that led also to smaller progression in the lateral direction in the coupled simulation. And you can also see the same thing here on the right side. So on the right side, there's the fire arrival time map difference. So essentially those red colors, they correspond to the regions where the fire from the coupled simulation appeared later than from the coupled simulation. So the interesting thing is that here, if you look at the very beginning of the fire, you will see slightly bluish colors corresponding to faster original propagation of the fire to the coastline. But later on, because of this interaction with the hydraulic jump, you will see more red colors on both sides, clear to closer to the northern and southern part of the fire, indicating the reduced growth in the lateral direction. So in a sense, what this particular scenario shows is that when you have limited fire growth in the downwind direction and you are interested just in the lateral spread of the fire, at that point, under those conditions, like I showed you before, when you have hydraulic jump, you may have a situation when the fire-induced circulation is going to actually limit the fire growth and is going to decelerate the fire progression in those active regions here in the north and in the south. So to sum up what we talked about today, we talked a little bit about the effects of fires on the environment, and I showed you an example of why they are important, why we investigate them, how important they are. We looked at the mechanism of fire-induced atmospheric perturbations, and we started from those idealized cases where we identified the inflow into the convective column being responsible for enhanced winds. But we also investigated larger scale events, the plume-driven plume-dominated fire, the creek fire, and wind-driven Thomas fire. And we also looked at those fire-atmosphere interactions in these cases, and we identified also the differences in terms of the pattern, non-local effects in wind-driven fires than local fires, also more diurnal pattern in the plume-dominated scenario than the wind-driven fire. We also looked at the impacts of fire-induced precipitation, and I showed you an example how that may lead to reduced fire spread and during the creek fire. And also we discussed the dynamic effects of the fire-atmosphere coupling when the fire interacts with the hydraulic jump. And that is an example that shows that those fire-atmosphere interactions may actually also slow down fire progression. And just the last comment is that coupled fire-atmosphere models can capture those fundamental effects of fire-atmosphere interactions, and that's how we can use them to investigate fire-induced winds, to assess their strength, and learn a little bit better about local weather modifications due to the fires. And that's everything. Thank you, and I'm ready for your questions.
Thank you so much, Dr. Kochanski, for this wonderful presentation. It's fantastic to see the research that you're doing with such clear and direct implications for accurately modeling fire spread. That's very interesting. And we're going to switch over to question and answer in just a second. But before that, I just want to say thank you once again and have others join me in thanking you for this presentation.